Have you ever wondered how your favorite app just knows what you like? Or how a bank can process millions of transactions a day without messing up a single one? Well, the secret sauce behind all of that is the database. And in this explainer, we're going to build our understanding of that magic from the absolute ground up, starting with the basics and taking it all the way to the massive cloud systems that run our world. So here's our roadmap. First, we're going to tackle why we even need databases to begin with. Then we'll put on our architect hats and design a blueprint for our data. After that, we'll learn the language to actually talk to the database, see how to make it rock solid and reliable, and finally, we'll look at how all these ideas scale up to power the entire internet.
All right, let's jump right in. To really get why databases are so important, we have to go back in time a little bit to what was basically the Wild West of data. It was pure chaos.
Just imagine every single department in a company, sales, payroll, customer support, all keeping their own separate lists in their own separate files. Sales has one customer address and support has a different one. What could possibly go wrong? Well, as you might guess, pretty much everything. It was a complete and total nightmare. You'd have the same customer's info in like 3 different places. That's data redundancy. And of course, they'd never all be the same, so you'd have massive inconsistency. If 2 people tried to update the same file at once, the data could just get corrupted. And security? Forget about it. It was basically non-existent. And this is where our hero comes in, the Database Management System, or DBMS for short. The best way to think about it is like a single super smart gatekeeper for all the company's data. Now everyone, payroll, sales, you name it, has to go through this one gatekeeper, which makes sure everything is handled in a secure, consistent, and totally orderly way. Okay, so we know we need a central system, but how do we actually design it? Well, before you build a house, you need a blueprint, right? It's the exact same idea in the world of databases, and that blueprint is called an entity relationship model. The first building block is something called an entity. It's really just a fancy word for anything in the real world we want to store information about. Just think of nouns, a customer, a product, an order. These are the core objects in our data universe. Now, just knowing you have a customer entity isn't all that useful. You need the details, right? And those details are called attributes. For our customer, that could be their name, their email, their address. These are just these specific properties that describe each one of our entities. And here's where it gets interesting. We connect the dots. See, these entities don't just float around by themselves. We link them together using a relationship, which is just how they interact with each other. A customer places an order. An employee works in a department. The relationship is the verb that brings the whole thing to life. And when you put all these pieces together, the entities, the attributes, and the relationships, you get this, your master blueprint. It's called an entity relationship diagram, or ERD. And this simple picture tells you a whole story. At a glance, you can see we have students and courses, and they're connected because a student enrolls in a course. It's a visual map of our data world. All right, our blueprint is done. Now it's time to actually pick up our tools and start building. To talk to our database, to ask it questions, to change things, to create things, we need a special language. And that language is SQL. So, we've got all this data sitting in our database. Now what? Well, we need to ask it some real questions, right? But you can't just type, hey, who are my best customers into a computer. We have to translate our human question into a super precise set of instructions the database can actually understand. And that translation is what a SQL query is all about. Let's just quickly break this down. We're telling it to select the customer's ID and the sum of their order amount. We say to get this info from the orders table. Then we group the sales together for each customer, order them from highest to lowest, and finally limit the results to just the top 5. It's like giving the database a perfect step-by-step recipe to get the exact answer we want. So we can put data in and we can ask it questions. But how do we actually trust it? I mean, how does a database make sure our information stays accurate, especially when tons of people are using it at once or, the power goes out? The answer is all about something called a transaction, which makes 4 basically ironclad promises. We call them the ACID properties. Atomicity means it's all or nothing. Think of a bank transfer. The money can't leave your account unless it successfully arrives in the other. Consistency makes sure the data always plays by the rules we set. Isolation means that if 2 transactions are happening at once, they won't mess each other up. And durability, that just guarantees that once a change is saved, it's saved for good, even if the system crashes a second later. Okay, Our data is now safe and reliable. The next step is to make it smart and efficient. And the process for doing that is called normalization. It really boils down to one simple but really powerful idea: getting rid of repetitive data. Take a look at this table here. To you and me, it looks okay, right? But for a database, that purchased products column is a total nightmare. It's got multiple items crammed into a single field. How would you even begin to search for everyone who bought a mouse? It would be super slow and just begging for errors. So the very first step is to get to what's called first normal form, or 1NF. The rule here is dead simple. Every single cell can only hold one value. So we just give each product its own row. And boom, just like that, the problem is solved. Finding all the mouse buyers is now incredibly easy for the database. But wait, now we have a new problem, don't we? Redundancy. We have John Doe written out for every single thing he buys. That's a waste of space, and it's risky. The solution is second normal form, 2NF. We just split the data. We create a customers table and an orders table, and link them with the customer ID. Now, if John Doe ever changes his name, we only have to update it in one spot. Much better. And we can take this just one step further to what's called third normal form, or 3NF. This just means we get rid of any details that don't belong. For example, the products table shouldn't need to know the supplier's name, right? It just needs to know the supplier's ID. So we move all the supplier info into its own suppliers table. What we're left with is this beautifully clean and efficient design where every piece of information has one, and only one, logical home. So we've built a really solid foundation, but how does all this work at the absolutely mind-boggling scale of the modern internet? How does an app with millions of users all clicking and posting and buying at the exact same time manage all that data? Well, at that massive scale, you run into this really big trade-off. That super strict ACID model we talked about, it's perfect for a bank, where you need every transaction to be perfectly consistent instantly. But for something like a social media feed, a different model called BASE often makes a lot more sense. BASE basically prioritizes being available and fast above all else, even if it means data is only eventually consistent. It means if you post a photo, your friend across the world might not see it for a couple of seconds. It'll get there, it just won't be instant everywhere. And this quote just hits the nail on the head. There's no single best database model. It is always about picking the right tool for the job. You'd want your bank built on an ACID system for sure, but trying to build something like Instagram on a strict ACID system, it would probably be painfully slow and impossible to scale to millions of users. And that really brings us to the biggest question for the future of data. With AI and all sorts of new technologies creating more data than we can even imagine, what are we going to prioritize? Will it be the perfect ironclad consistency of the ACID world, or the lightning-fast, massive availability of the base world? Or is the next huge breakthrough going to be a new model that somehow gives us the best of both? That right there is the challenge for the next generation of data architects.